Hello and greetings everyone, dear Energetics 2022 conference participants. I'm Nenad Petrovic, a teaching assistant at the Faculty of Electronic Engineering, University of Niš Serbia, Department of Computer Science. In what follows, I'll present you my paper which is entitled Machine Learning Enabled Smart Grid Services using Weka in Java. It is already widely adopted that machine learning enabled services represent one of crucial factors when it comes to both novel innovative user scenarios within smart grids or improvement of the existing ones, such as predictive maintenance and, on the other side, cost-effective energy management. In this paper, it is focused on Weka API adoption for supervised machine learning in Java, which can be further exploited for implementation of IoT-enabled machine learning architectures and services in synergy with Orion Fever Context Broker. After that, the approach is evaluated on publicly available online datasets for two case studies. The first one is classification-based smart grid stability prediction. The second one is regression-based household energy consumption prediction. Now, let's see some basics of supervised machine learning. It represents a set of methods and algorithms that enable prediction of target selected outcome variables, observing huge amounts of previously collected measured data within the data set. There are two types of data sets. The first are training sets, which represent collection of samples with known outcomes that are used to adjust relevant hyperparameters, which actually make the model itself. On the other side, we have test set, which is used in order to evaluate the previously trained model. As I mentioned, there are two types of parameters. The first are hyperparameters that control the learning process, and on the other side we have weights which are actually derived during the process of training by observing the training set. Moreover, we have cost function, which examines how much the predicted value actually is distant from the expected one, which can be further explored to adjust the weights proportionally to the amount of provided hyperparameter value. Two most common techniques which are used for supervised machine learning are classification, in case when we want to predict categorical outcome or label, and on the other side regression, when we have continual numerical integer or real values. Now let's see some performance metrics. On the upper part of the slide we can see classification, aiming performance metrics, which are precision, recall, F-score and accuracy. In this paper we'll use accuracy. We have on the left hand side the abbreviations which are used for the variables within the equations. On the lower part of the slide we have regression related performance metrics like relative error, absolute error and root mean squared error. Now let's see some key concepts of Weka API in Java. It actually represents an open source machine learning framework which actually offers a set of classes and functions which enable to implement supervised machine learning. Here we have instances which represents a data set itself, CSV loader which is used, which aids the process of importing CSV data from the dataset into instances. We have distinct instance, which is one sample from the whole dataset. We have classifier function, which are collections of various supervised machine learning algorithms for both classification and regression. And we have evaluation methods, which enable actually to estimate the performance of the trained model. Here you can see the flow of machine learning related steps using Weka API in Java. We have interface which incorporates all these capabilities offered by the libraries that are together contained with Weka. And the first step is actually loading data from CSV file, as you can see here, from external sources like publicly available datasets. After that, we have a set of instances where we select the target variable, the one that we want to predict. After we have labeled dataset, we can train the predictive model by calling we instantiate first the desired algorithm, which is here called model. It can be either regression or classification method, and we call build classifier for the dataset as input in order to create the model. Once we have the predictive model, we can evaluate it by using evaluation method and cross-validation of the model. And finally, it is possible to apply the model itself on new, previously unseen samples. Here, on the other side, we have integration with Fever Context Broker, which is an efficient platform combining various open source solutions for smart cities and can be accessed via REST API. Here, in these two listings, we can see how actually the flow of communication of IoT devices would occur. So each time some event occurs, we have the first type of request where some data is modified or inserted. In this case, the stability of device can become zero. Actually, some device becomes unstable within the grid. On the other side, we have devices who listen on the changes of some parameters, like stability in this case, so they will be notified each time some change of stability occurs. We can have different types of service applications, like mobile applications used by household people from household, or either some IoT devices which are actuators can receive these notifications and act accordingly, like turning some device off if there is some potential danger of damage or some other instability that or maybe even huge energy consumption which can be reduced by entering some devices to power saving mode. Here is the flow of communication. The overall system architecture. We have a Java Enterprise Edition based system which actually is accessed via a GSF web application client. Here user can provide some inputs or visualize the data from the database, which is MySQL database. Enterprise Java business classes are used as business logic layer, and they actually perform operations on objects which are persisted within the database using Java Persistence API and Hibernate. On the other side, Weka API is used for predictions during the business logic process execution, and on the other side, when some conditions occur, business logic sends requests to Fever Context Broker. Furthermore, these requests can trigger some notifications to be pushed to devices who are listening on given URL addresses, like stability change, so they can act accordingly. Here is more detailed overview of implementation in form of UML class diagram. On the left-hand side, you can see the software part related to the application itself, Java Enterprise Edition application. On the right-hand side, you can see the experts from the code which represent the predictive model and how it is used on the lower part of the slide. The upper part represents the process of training according to the given flow here, and the lower part actually is how we make new predictions using the previously trained model. For case studies, we use two publicly available online datasets. The first one is stability prediction case study, which actually represents 16,000 records, and we have a set of inputs presented here. Classification approach is used due to categorical outcomes, which can be stable or unstable. So the input factors are reaction time for participant nodes, nominal power, coefficients of rise elasticity, while the output is characteristic differential equation maximum real part of the root, and if it's positive then we'll have stable state, otherwise it's unstable. On the other side, we have household consumption prediction case study, publicly available dataset for 768 buildings, 12 different types of shapes. We have consumption prediction using regression for continuous based value outcomes. And here are the prediction factors that are relevant to the household, like relative compactness, which is ratio between volume and surface, room size, wall size, glass surfaces, roof size. On the other side, we have house height, orientation of the house, where it's placed north, east, west, or south. We have a glass surface distribution, like one or more glasses, and the outcome is either heating load, the heat consumption, actual energy consumed during winter for heating, and on the other side, summer cooling load, like cooling energy consumption during summer, but heating is energy consumption during winter. When it comes to evaluation, there are different algorithms compare for classification, we can see that the best results were achieved when it comes to prediction quality in case of J48 algorithm, and it gives quite low training time, like 28 seconds, while the other algorithms show either worse performance or much longer training time. When it comes to regression method, we use linear regression. It had like around 5 seconds of training time and root relative squared error as given here. So as you can see, the models were evaluated considering two aspects, both the training time, the processing time for adjusting the model, and on the other side, the quality of predictions themselves. For classification accuracy was used like the ratio of between the correctly classified examples and the total number, while for regression we have relative error and root relative square error. To sum up, in this paper it was demonstrated how machine learning based techniques can be incorporated within information systems for IoT based smart grid management. For case studies we used two publicly available datasets. One is stability prediction using classification, and the other one is actually a regression based energy consumption prediction, while we make use of Weka API in Java for purpose of implementation in synergy with Fiverr Context Broker. As outcome we have two supervised learning predictive models with satisfiable results, and when it comes both to prediction performance and execution time. Thank you for your attention.